Looking at chapter 4, which starts with integration. So the first half of calculus was all based on the idea of derivatives. So we looked at things where you had a curve and we were trying to find the equation for the tangent line or the slope of the tangent line. The second part of calculus deals with area under the curve, and the idea is we're going to work backwards. Instead of finding derivative, we're going to do what's called the integral, and we're going to find the area. And we're going to find areas of all different sort of shapes there, not necessarily ones we have geometric formulas for. So that's where we're headed. The first part of this, so we kind of do this chapter out of order because the first piece that's in 4.3 talks about finding areas using formulas that you already are familiar with from geometry. So you kind of need to know what the notation is. So the integral symbol is this sort of elongated S. It stands for a sum. You're going to end up adding up a bunch of areas there, so that's why they kind of use that notation. There's a lower bound or a lower limit. That's the one that's on the bottom, and then there's an upper limit, which is the number on top. The bottom number and the top number don't have to be in any particular order in terms of the lower bound could be smaller, the upper bound could be bigger, or vice versa. They could be the same number. And then the other piece of this is that you have your function. Now this dx that you have on the end here, if you remember when we found derivatives, so if you had, I don't know, something like that, if we found the derivative, we could write this a bunch of different ways. We could write it as y, we could write it as dy over dx. And then you would take your derivative and get something like that. If I solve this for dy by multiplying both sides by dx, it's the derivative, and the dx is called the differential, and it just tells you which variable that it is that you're integrating, what's the variable that you're working with. So dx means you're working with x's there. So that's what that value is on the end there, that dx. You kind of, for this point, you kind of ignore it at this point. So if I want to find the area under curve from A to B, right, so this little piece in here, and there's my function f of x, the area formula would look like that. I would integrate from A to B for f of x dx. All right. So as I said, the first piece of this, we're going to deal with geometry formulas that you're familiar with. So if you look at the properties down below here, this holds true for any kind of integral here. If I want to flip the bounds around, instead of going from A to B, if I want to flip those and make that from B to A, you just need a negative out in front. It's the opposite. If I integrate anything from A to A, think about it. I look at that, I have no base or no space for the base there, so that's 0 times whatever the height is, which would give you 0. If you look at the next property, if I want to take this area and I add this area to it, it gives me the area from A to C, both of those two things together. So that's what this property is telling you. You can break it apart into pieces there. The next one tells you if you have a constant term multiplied by a function, you can take that constant term and put it out in front. That's kind of the same idea as when we had something like this. If you had y is 3 sine of x, if you wanted the derivative of that, you kind of just left the 3 out in front. You said to yourself the derivative of sine was cosine. Same idea with integrals. You can put that constant term out in front and multiply your answer times that. And then finally, the last one just tells you if you have a bunch of terms either added or subtracted there, only addition and subtraction, not multiplication or division, you can separate it. You can find the area under this curve first, and then the area under the second one using those same bounds from A to B, and just add or subtract depending on what those symbols were to start with. So the properties, I don't think they need a whole lot of memorization. I think there's kind of obvious what you're going to do with those. All right, so let's look at the next page. This is different ways that these problems could be set up. So the first one is they give us a diagram here. And I will say this much, I don't know that we talked about it in the on the first page there. If the area of the figure is above the x-axis, and you're going from left to right, just like you read a book, that would be a positive area right in there. If I look at the area going from left to right, so if I'm going from here to here now, that area is below the x-axis, so that would be a negative value. If I go from right to left, so if I go from right to left and find this area, going in this direction, that's going to be a negative value. Same with this one over here. If I go from here to here, going right to left, it would be a negative value. And if I look at this last one here, if I go from right to left in this direction here, that area is negative, but going from right to left is also negative, so negative and a negative would make that value a positive. So area is one of the applications of this. It's not the only application. So sometimes you can have negative values, and we'll call it area, but it's really not area that we're referring to. Okay, so let's find this first one here. So we're looking for the area from 1 to 5, so from here to here. And if you look at that, it's just a quarter of a circle. So you have an area formula for that. 1/4 pi times the radius squared. Looks like the radius is 4. So 4 squared would be 16 divided by 4 is going to give us 4 pi for that area. We went from left to right, so that's a positive value. For the next one, they said from 11 to 5. So here's 11. Here's 5. So they want this area, but they want us to go in that direction. So the area is going to be a negative. And that's a triangle, so half the base, which is 6, and the height looks like it's 4, so it's going to be negative 12 for that area. All right, and then the next one, they said go from negative 6 to 1. So from negative 6, that looks like that's right there, and positive 1 is right here. So it's a quarter of a circle, which we already know that formula. We just found that in number 1 there was 4 pi. And then this area right here is going to be a negative value because it's below the x-axis and we're going from left to right. So that looks like it's going to be 1/2. My base looks like it's 3. And the height looks like it's also 3. So it looks like negative 9/2 for that. And then the next one is from 5 to negative 3. So again, we're going from right to left. Here's 5, here's negative 3. So it's that semicircle. If the area of a quarter of it is 4 pi, all of it would be 8 pi for 2/2 of that semicircle. But I'm going from right to left, so it'll be negative 8 pi for that one. And then we're just sort of combining some of this together. So let's see, number 5, we're going from 5 to negative 6. So here's 5, here's negative 6. So the semicircle, the triangle, the semicircle we just found, going from right to left, so that'll be negative 8 pi. And then the triangle, we just found that area was 9/2, but going from right to left, that's going to be minus a negative or positive 9/2. And then finally, they want all of this area. So the first one was negative 9/2, that's the little triangle here. The semicircle we said was 8 pi. And then this last triangle here, where was that area? Oh, it was up here. It was negative 12 going the opposite direction, so it's positive 12. All right, you can leave it like that. You can combine the 12 and the negative 9/2 together if you like. All right, so that's one way that you'll see these problems. Just find an area, and like I said, they'll all be geometry formulas. Triangles, semicircles, might have a trapezoid in there. The second way they might ask you to do this is by using the properties. And using the properties, they'll give you the values for some of these integrals here. So from 0 to 5 is 3, and from 5 to 7 is 8. So if I go from 0 to 7, I'm just going to add those two values together. Right, the two smaller areas added together give you a larger one. For number 8, they switched the bounds around here, so now we're going from 5 to 0. So if 0 to 5 is 3, 5 to 0 is going to be negative 3. The bounds are the same. Doesn't really matter what the function is. If the bounds are both the same, your area is always going to be 0. And then finally, this last one has a scalar multiplied by, so it's going to be 3 times, and then the area from 5 to 7 was 8, so we get 24. Right, and then the last piece, they don't give you a graph of this, but if you go through and you graph this for yourself, we're looking at this equation, which is your y equals, or here they tell you f of x equals, so y equals 4, it's just a horizontal line, and we're looking for the area from 1 to 3. So I'm looking for the area of that region there. Well, the base is 2, the height is 4, so the area is going to be 8. So you can always look at the area by graphing this. The next one, y equals x plus 2. So if I go through and graph that one, starting at 2, I have a slope of 1. It's a sad little line there. All right, and we're going from 0 to 3. So this height, if I plug 3 into the equation, I'm going to get 5. And this side was 2. So let me just fill in what we have here. So this is 2. That's 5. That part there is 3. And this is the shape that I'm looking at. So I'm looking at the area of a trapezoid. You really don't need this part of the graph there if that's confusing. So area of a trapezoid is 1/2 the height times the sum of the bases. So 1/2. Now the height's the space between the parallel sides. So those parallel sides are 3 units apart. And then the bases are the parallel sides, which have a height of 2 and 5. So it's going to give me 21 over 2 for that area. And then finally, this last one here, y equals the square root of 4 minus x squared. That's just a semicircle. My radius is 2, so this is what I'm looking at. So my area is going to be 1/2 pi. The radius squared, which is 2 squared. So 4 times 1/2 would give us 2 pi for that. So you may see some problems where you have to just go through and sketch the graph. And once you sketch the graph, you have an area that you know how to find. Now these are a little bit trickier here. They give us sine x and from 0 to pi has an area of 2. Now eventually we'll be able to go through and find that using integration. Right now we don't know that. So I'm just going to do a little graph over here of our sine function. Just remember what it looks like, because that's going to help us for some of these problems here. I'm going to do a little bit in this direction here too. Maybe I'll do 2 periods. There we go. All right, I'm pretty close there. All right, so they said from 0 to pi, so this region right here has an area of 2. So that's what's given to us in the directions. And then they said find these other areas. Well, if I go from pi to 2 pi, now they're looking at this piece down in here. You can figure out that area. If this first part's positive 2, this one's going to be negative 2. It's below the x-axis. For number 2, which is over here, they said go from 0 to 2 pi. So from 0 to 2 pi, you have a positive 2 and a negative 2. Gives you an area of 0. And then they start, getting a little fancy here and dividing this thing up. So if we go from 0 to pi over 2, here's pi over 2. Instead of having an area of 2, you have an area of 1 because you have all that symmetry going on with that one. For number 4, you actually have to use one of your properties for this. We had a property that said anytime you have addition or subtraction, we can separate this and make this 2. And then sine x. Well, 2, we can graph that. We have a height of 2, and we're finding the area from 0 to pi. So it's just a rectangle. Anytime they give you a constant term, added or subtract, it's just a rectangle. So that length is 2, that height is pi, that height is 2, so that area is 2 pi. So the first piece has an area of 2 pi, and then sine of x from 0 to pi, back in the directions, they told us that was 2 up here. Sorry, homework up. All right, so the next one, you have a scalar out in front, so that 2 stays out in front, and we can think of sine x from 0 to pi is just 2, so we can carry a 4. This one, they change this inside, x minus 2, that just shifts the graph right 2 units. But then look at the bounds. Instead of being 0, this bottom bound is now 2, which shifted right 2 units. And pi plus 2, right 2 units. So the whole graph is shifted to the right 2 units, but nothing else has changed. So it's still going to have that same original area of 2. The next one, negative pi to positive pi. So negative area, positive area gives us 0. And then number 8, this one looks tricky, but if you think of what your cosine graph and sine graph really look the same. Let's see. Right, so my cosine graph starts at 1, ends at 1, halfway between we're at negative 1. Right, but it's the same shape, it has the same sort of areas, it's just shifted to the left or to the right. So if I find the area from 0 to pi, I'm looking at this, and I'm looking at that. One's positive, one's negative. It's going to give me an area of 0. And then finally, the last piece says sort of generalize what's going on here. I'm just going to slide this a little bit because I still want that sine graph up there. So let me erase a couple of these things here. All right, so the last piece says, suppose you have any positive number for k. If these two numbers on the ends of the bound for the sine graph, what are you going to get for your answer? So think about it. We went from negative pi to positive pi. This area was negative. This was the same thing, positive, canceled out. If we went from, negative pi over 2 to positive pi over 2, that area would be 0. That area would be 0. We'd still get 0. So this is always going to give you 0 because sine has symmetry with the origin, which means it's an odd function. So long as those bounds are just opposite values there, the area is always going to cancel out. You'll have part that's positive, part that's negative. All right, so what you're doing then for homework is the problems on this next page here, homework 4.3. It's all using the properties. I'll warn you for this first part, make sure you see this part of the directions. Find the following integrals if possible. Not all of these are possible. Right, so you may have some that you cannot find. You don't have enough information given. So make sure that you see that. That was a common mistake that other people were asking. All right, these down here you're going to just graph. If theta drives you nuts, make it an x. Same with this one here. Make it x dx if you don't like theta. Right. This one you're using the property up here. They give you a value. Might want to do a nice little sketch of y equals x cubed. Right, and then this last part is just like we did in the beginning there. You're finding those areas. You'll have triangles or trapezoids or rectangles or semicircles that you're trying to find the areas for there. Okay.